This video here is meant to serve as an introduction of where electric current would come from. Now, most of us have heard about current because it's the kind of thing that sort of comes out of the walls of our homes and runs things like our toasters and our computers and so on and so forth. So in this video here, we're going to try to figure out where it comes from. So before we get going on where electric current comes from, let's make a little thought experiment right here using a sketch. What this is here is a capacitor. And what I'm going to do with the capacitor here is I'm going to connect it to a piece of wire that's bent around in these two shapes here. And the wire that's connected to the capacitor here is going to have a little break in it. So I'm not going to let full conductive path go all the way around the capacitor. And furthermore, let's just say that the capacitor is fully charged up. This side has a bunch of positive charges. This side has a bunch of negative charges on it. So the issue then is when I connect this wire with the break in it to the capacitor, what happens? Well, sort of like you might think, the positive charges start to bleed off this capacitor here and just sort of start to fill. Let me not draw the charges out there. Let me actually draw them in the wire here. They just sort of fill the whole wire here with positive charges. And likewise, the negative charge is going to go over here and sort of fill this wire here with a bunch of negative charges. So that's what sort of happens when you connect a broken wire to a capacitor. Again, there's a break right there, so there's no conductivity all the way around like that. That's sort of what will happen. And that's generally what we've seen in recent videos about how charge flows when we connect things. Just positive things sort of all become positive, negative things all become negative, and off we go. So keep that in mind. But now the next picture, I'll just erase that just as quickly as I drew it here, is what happens if we take that charged up capacitor then like this, and we ran it through another piece of wire like this, but this time the wire, I actually let it be connected all the way around like this. All the way around. So here's the wire here, and I need a little bit of thickness on this wire here, so that's why I'm not drawing just as one pen line like that. I'll sort of draw it like this, and let me get the capacitor just a tad bit longer like that. And just like before, we'll just say that this plate of the capacitor was charged fully positive, and this plate of the capacitor was charged fully negative like that. So what's going to happen now? Well, this is what I'm shooting for here. I am shooting for this wire to be completely closed like that, but let me just assume that it's broken for a second like I did before. And so what will happen is, of course, the positive charge will fill this wire, and negative will fill that wire. But now let me go ahead and connect it, almost like there's a switch here. Let me just go ahead and connect this wire here to this side and to this side like this. Now, what happens now, something in a very brief period of time, something like within 1 nanosecond or so, so 1/1000th of a second or so, there's something that happens very quickly. In that billionth of a second, what happens is that as the capacitor starts to lose its charge, what we have here is the negative side, the positive side here goes all the way around and sees all these negative charges, or alternatively the negative charges see all these positive charges over here, and they would like to neutralize each other. But again, within that billionth of a second of me closing the switch or letting that wire become completely connected down there, the charge distribution looks something like this. There's sort of going to be an overabundance of positive charges all in this region of the wire, and overabundance of negative charges all in this region. And you can sort of think about it because this is where the source of the charge are coming from. These capacitor plates are fully charged, and this negative side over here is fully charged with negatives. Those are sort of the source of the charges. So what we see happen in that billionth of a second is the charges tend to accumulate around their sources like that. They definitely spread all the way out, but just a little less so, a little less abundant as it sort of travels around the wire. Same signs in here like this. So they're very abundant here and a little less abundant as we go all the way around the wire like this. And it turns out that right here in this midpoint between the positive and negative charges in a region ever so small here, there's actually no charge. So the charge takes on a really bizarre, and let's just make sure we have this picture here, non-uniform charge distribution. Now you can contrast this charge distribution with the one that I drew at the very beginning of the video where there was a gap here. When there was a gap in the wire here, the charge was nice and uniform. In other words, the positive charge is spread out equally all over their section, the negative charge is equally all over their section. But now it's very non-uniform. And again, only for that billionth of a second in there. Because what starts to happen after a billionth of a second is the capacitor is just going to start to run out of charge. All these positive charges and negative charge will just sort of start morphing and traveling through and just become neutralized. But at least for that billionth of a second, this is sort of the picture that we see. Now, what we have to do now is imagine a piece of wire then that sort of had a lot of positive charges over here, a lot less and less and less until it reaches no charge here. Then a few negative charges pop up, more and more negatives, more and more and more until we get a whole bunch of negatives over there. Let's imagine a piece of wire that looked like that. Okay. Again, this is only for that billionth of a second, but it's the clue about where electric current comes from. So what I'll do then, let's zoom in now and really look at that wire. Because we all know that wires are the carriers of electric charge, extension cords, and that kind of thing. So let's just get a nice piece of wire on there. And let's imagine then that the region over here was just loaded with positive charges, and a little less so here and a little less so here. Then there's that gap in the center where the nothing exists, or not nothing, but no charge rather. And then just your negatives were here and a few negatives here, and then the negatives were really a whole bunch of negatives right over there. Same sort of thing. So nice and symmetrical like that, but keep in mind, this is just that wire I've straightened out. There's a lot of positive charges here, a lot of negative charges here, but as we go over this side, the positive charges sort of dissipate. They're not so concentrated. Likewise for the negative charges till we get to the center when there's nothing in there again. And again, this is all what's happening in that billionth of a second. Very short amount of time like that. So what we have then is a wire like this, and if you imagine what a wire is, well, this analogy or this example works with any shaped wire, but of course we know that wires are sort of round, extension cords are round, and pieces of copper are round. So really what this ends up being here is sort of a charged ring of positive charge. This little slice here is a charged ring here, and this is a charged ring here. And this is a negatively charged ring, and this is another negatively charged ring, and there's a big negative charged ring over here where that negative charge is really concentrated like that. So what these become then, if we look at slices of this wire here, is these are actually just a continuous band of charged rings all next to each other, each one having various amounts of charge on it. That's what the wire becomes. And yeah, these charges are on the surface as well. So what does this tell us then? Well, if you remember from a couple of videos ago, we did talk about the electric field outside of a charged ring. So if I have a ring like this, which is charged with a bunch of positive charges on this, I hope you remember this from those videos here, there's a bunch of positive charges on this ring here, positive, 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 there's actually going to be an electric field out here that points away from the ring. And the more charge that's on this ring, the stronger this electric field is going to be. And the less charge on this ring, the less strong the electric field is going to be. Now, if we have a negative ring over here, that's sort of oppositely charged than the positive one, obviously. So suppose we have a bunch of negative charge on this ring right here. What we're going to see either here or here, for that matter, is electric fields that point towards the ring and towards the ring. And by the way, on the positive ring over here, if I go to the side out there, there'll be an electric field pointing away from the ring. Remember, same rule applies. Electric fields point away from positive charges and towards negative charges like this. So this is sort of the situation that we see. This is a reminder of the electric field some distance away from charged rings. They look something like that. Okay. So then we look at, well, remember what the wire is here, this non-uniform charge distribution that exists for a billionth of a second. They're charged rings. So what happens, say, if we look at a point right here, say, there's going to be an electric field pointing this way because of this charged ring. And there'll be an electric field pointing this way because of this charged ring, but it's not quite as large as this electric field because there isn't as much charge here on this ring. So all net told, in this region right here, inside the wire there's going to be a big electric field, not a big electric field, I'm going to say a net electric field that points to the right. So this purple line here will be that net electric field. There'll sort of be a net electric field, which is the sum of those two black ones that points that way. And likewise, in this region right here, there's going to be a big electric, not a big electric field, but a larger electric field because of this charge ring. And there's going to be one pointing the other way because of that charge ring, but not as big because there's not as much charge there. Again, that's what this non-uniform charge distribution is all about. And so there'll be an electric field pointing this way, in this region of the wire. And even in this intermediate region here, where we said that no charge exists in that sort of transition from positive to negative, there'll be an electric field pointing this way because of that positive charge. And this negative charge, remember, the electric field, because of it, is going to point that way. So that electric field plus that electric field is going to create a net electric field towards the right also. So it turns out that no matter where I look inside of this wire for that billionth of a second, there's a net electric field here, the purple one, the green one there, and everywhere inside the wire there's going to be a net electric field that points to the right, everywhere inside that wire, because we imagine those charged rings with that non-uniform charge in there. Electric field points to the right like that. So then there you go. What is it about what happens inside of a wire when that wire has a net electric field in like this? So here's that wire again, like this, and like this. And so what happens in here, if you remember, we go to the moment, I think the very first video we made in this electricity series right here, there's a bunch of ions, protons, if you will, positive charges, whatever you want, that make up the crystal lattice here, that are what copper. So all these green dots here would be, say, copper ions in a piece of copper wire that you get at Home Depot. And all these little red things in here, these are all the electrons, the sea of electrons that are all ready to go and move around in there. Very easy to push them around. These electrons can be thought of as almost like gas molecules. They're just freely floating around there. But the difference now is that there is an electric field, a persistent electric field, all inside this region here that's created by that non-uniform surface distribution that results from putting it on a capacitor like that. And if you remember now, what do electrons do when they're in an electric field? Remember, the force law is minus Q times E, something like that. There's a minus sign because of the negative sign on the electrons. So that means that the electric field points to the right. All the electrons are going to start moving to the left. And so what will happen, like this little red electron right here, is this can start drifting to the left. And this one right here is going to start drifting to the left, but it might run into that copper ion, no problem. It'll just bounce off of it, and when it gets caught up in the electric field, it'll just start keep going this way. And this electron will go this way, and this electron will go this way, but it might run into this copper ion and bounce back, and then it'll keep going again. And this one has no obstructions, it'll keep going like that. So what you get, all these electrons start to drift towards the right. So we call it the not towards the right, to the left. Electron drift to the left. And that's exactly what happens in a wire, and that's where currents comes from. So the nature of a current then, nature of a current comes from E field inside of a wire. And the E field inside the wire was put there by putting a voltage across the wire, in the case that we saw a capacitor plate. So you see a charged capacitor. See, it's very important then that this charge distribution is non-uniform, and it's also very important that, at least in the case of the capacitor, something that exists for a billionth of a second. But you're thinking, now wait a minute now, you can leave your computer on for hours and hours at a time. What does this 1 billionth of a second have to do with it? Well, remember, it also comes to another difference I think we alluded to at least for a second in a video a while back in the series here that had to do with batteries and capacitors and stuff. So now the issue is like, what happens now if we take that same piece of wire again that looks like this and looks like this, and we connect it to a battery now, not a capacitor. So remember, either a battery or even like a power plant or something that has more charge in it now. That's really the difference here between a battery and just a capacitor. There's more charge in there. So what happens then is that, all told, what the battery does is maintains a potential difference across these ends of the wire. So this is our favorite 9-volt battery once again. This would be the plus 9-volt side, because that's where this lead of the battery is connected right to the wire. And this would be the 0-volt side right here, because that's where the negative lead is connected to the battery like that. And so what you'd get then is you'd get an electric field, as we said before, that's established inside the wire, and you can even compute the magnitude of it. So if this wire here had some length of 2 meters, and it's 9 volts you have across it, we have a relation from capacitors that V is equal to E times distance like that, or electric field is voltage divided by distance. So in the case that we have here, the voltage is 9 volts, and the distance is 2 meters. So the electric field inside that wire there would be 4.5 volts per meter. And there's even another example of where that unit of electric field of volts per meter comes from. Sometimes you or your book and your instructor might call it a Newton per coulomb, but the units themselves are equivalent. That's exactly where that electric field would come from. And in terms of that 1 billionth of a second in the capacitor and that sort of thing, you have to hypothesize, though, that if this is actually the case that's happening here, there's 9 volts here and 0 volts here. What does that charge distribution look like on the surface of the wire? Well, once again, it's going to be very concentrated positive charges over here, and no charges there because it's negative. But as we move sort of to the right here, the positive charge contribution just sort of dies and dies and dies until it sort of becomes 0 right there. So very concentrated here, not so concentrated as you go down, and that is the origin of that surface charge, of those charge rings. That here's a charge ring here, and here's a charge ring here with a little less charge on it than that one has, and here's a charge ring over here on the surface with less charge than that one, and less charge as it goes down. So there's all those rings there, and all those little electric fields caused by those rings are exactly the origin of those black lines that you see inside the conductor. So you have the conductor with the electric field inside of it, and the electrons are going to move opposite to the electric field lines, and that's the nature of a current then. All said and done, the nature of what a current is a flow of electrons. In this case here, due to an E field. And that's exactly what a current is and where it comes from.